So when we say this limit is equal to 1, what we're saying is that these terms of the sequence eventually are very similar to each other, and we can consider them as approximately equal. For any positive c, right, what we're saying is this limit being equal to c is a sub n is roughly equal to a multiple of b sub n eventually, right? So there's a large enough n where we can consider them as close as possible. This is just what the limit of a sequence means, right? So what this really is trying to convey to us is that whether we're looking at the case where a sub n is literally equal to b sub n, or a sub n is a multiple of b sub n, they cannot diverge from each other. So if b sub n is getting larger and larger and larger, so is a sub n. If b sub n is getting closer and closer to 0, so is a sub n, and so on, right? So they can't diverge from each other is really the key. So these sequences are in step. And there's some tenuous connection here now that we're not going to get into for how this conveys into the series, right? But one really important thing is that these two sequences can also march off to infinity together. So just as we said, the a sub n being a multiple of b sub n means they eventually converge to the same spot. That can mean convergence to infinity, which is bizarre, right? But it makes sense, right? If one is getting extremely large and the other one's getting extremely large, just because L'Hopital's rule is going to give us a finite value for c, doesn't mean the series themselves aren't getting very large either, right? They could be getting very large. So why is this one so helpful? Why is the comparison test so helpful? Or the limit comparison test? We just need to find, so how to use it. The limit comparison test, I'm abbreviating it as LCT. So here what we're going to do is we're going to find a series b sub n that is eventually like a sub n. So the b sub n is eventually like a sub n or a multiple of a sub n. So the terms of b sub n, the terms b sub n have to be something like a sub n or a multiple of a sub n. And find the limit as n approaches infinity of a sub n over b sub n. This is only conclusive if that limit exists. Remember, if the limit doesn't exist, we don't know anything about a sub n and b sub n with relation to each other, so we can't say whether the series that we're testing converges or diverges. All right, so here we go. Let's do an example. Does the series from n equals 1 to infinity of the square root of n squared plus 1, all under 1, converge or diverge? Okay, so here's our reasoning. 1 over square root of n squared plus 1 is eventually like 1 over n, or square root of n squared, which is 1 over n. So our conjecture is the series diverges because it's eventually like the harmonic series. Okay, so let's find the limit as n goes to infinity of a sub n over b sub n. And that means we're going to have 1 over the square root of n squared plus 1 all over 1 over n. And that looks like the limit as n goes to infinity of n over the square root of n squared plus 1. And what can we do here? We can do a number of things. We can either use dominance, right? Or we can use dividing by the highest power of n. So for instance, this looks like n divided by n over n squared, or 1 divided by n. And if we pull that in, that should look like was the limit as n going to infinity of 1 over the square root of n squared minus plus 1 over n squared. Because if you're pulling it inside the square root, that's a nice shout out to chapter 2, remember that? Okay, so then this means this is the limit as n goes to infinity of 1 over the square root of 1 plus 1 over n squared. Okay, now it's pretty clear how this must be converging to 1, right? Because in the limit, this is going to turn to 0, and we have 1 over the square root of 1. Okay, so we're pretty certain that this limit is equal to 1. So eventually, since a sub n is close to b sub n, eventually, by the limit comparison test, I'm going to abbreviate that as LCT, the series n equals 1 to infinity over 1 over square root of n plus 1 diverges, since we compared it to the harmonic series, which is known to diverge. Okay, so those are all the pieces put together. You can apply this pretty generally to virtually any of the series that we've covered so far. And it is just really nice because this is easier in that you don't have to worry about comparing it to a series directly by comparing the terms in terms of inequality, right? Because it can be hard sometimes to get that accurately. Which series has bigger terms than the other? It can be helpful to use Desmos to compare the series, the terms of the series, and see them visually. So that can also be helpful. But this one is a really good tool because it's completely analytic. You don't have to worry about graphing or having any intuition beyond working with sequences and what you know about limits. So in the next set of videos, we're going to move on to the next section, 11.5, and talk about alternating series. And that's a whole nother exciting world of infinite series. And it turns out they work out very nicely.